Alright guys, so significant figures, something you've probably never heard of, but is something that gets really important, especially as you go through science. We definitely will be using it in this class, especially as we get more math-oriented second semester, and you'll definitely see it when you get into Mrs. Cook's class, if you start taking some of those classes where you see more math like chemistry and physics. So the point of significant figures, which a lot of people get very frustrated with, I'm not going to lie to you, this is quite possibly people's least favorite topic that we go through the whole year. And unfortunately, it sticks with us all year. But the point of the significant figures is to show a correct amount of accuracy in numbers that we know. So it basically tells us where should we accurately round to when we do these math problems. Do we round to the 10th, to the 100th? What should we do? Where do we show how accurate we actually know this information is? Because if you show more decimal places or more numbers in a figure than you actually know is correct, that's technically lying in a way, because you can't for sure say you know what those numbers are past a certain point, which I'll explain more as we get through. But either way, the point of this is to show a correct amount of accuracy. So bear with me in this. I will explain the best I can on this video, and we are definitely going to spend a few days practicing this, but I want to give you the main rules. You're probably going to be confused. Unfortunately, that's how everybody is. I always was too when I first learned this. But stick with me. Please listen to the video. Do your best you can. And then we'll go through this more as we are finishing up this chapter the next week. Alright, so we're going to go through looking at what numbers are significant and non-significant. So essentially, significant means that it is an important number in the figure. It is something that needs to be there. It shows a certain amount of accuracy. Where non-significant are ones that they hold a place, and they don't really supply any kind of importance when it comes to how accurate the number is, which sounds really confusing, but I'll go through these, and there's 6 different types of significant and non-significant. There's 5 on the screen and then 1 on the next. So forgive me, I'm going to be using the pen. I only have my mouse pad. I do not have an actual mouse, so the writing's going to be a little bad here, but I'll just put S for significant and NS for non-significant. So let's start with the bottom middle here. So this right here. This is definitely our easiest one to identify if it's significant or non-significant. Any number that is not a 0, so we have a 4 and this number and another 4 and a 5, they are significant numbers. So go ahead in your notes and write significant. I'm going to write an S because I'm clearly struggling with this mouse pad. But if it's not 0, that automatically makes the number important. So those are the easy ones. The rest of them have to do with zeros. They can get a little bit tricky. Once you learn the rule, it's not awful, but it takes a bit to get used to. So another one that I'd say is probably one of the easier ones is any 0. So we'll start at the top right here. Any 0 between non-zero numbers. So we have these zeros here. They're sandwiched between 2 different 4s. They're connecting these 2 4s. They are also significant. So, goodness gracious. Okay. There's also significant. So go ahead and write significant in that top right box. Because they are connecting to significant numbers, you can't really just take them out, because then it's going to make a whole new number. So they are important. So that's why they are significant. Any cosmetic zeros, so this bottom left box right over here, so this 0 here, any cosmetic 0, which means it's a 0 before the decimal place, and there's no other number there. So this is just a 0. Like if I were to write this number out, I could put the 0 there, I could not put the 0 there. It wouldn't make a difference. It's going to be the same exact number. So because of that, this is non-significant. So go ahead and write non-significant in that bottom left box there. So a cosmetic 0, which is ones that are just in front of the decimal place without any other number, they're not important, so they're non-significant. The other 2 are, or I guess one more that's not as bad, but so we'll go to that one, and then we'll get to the last 2 that tend to throw people off the most. So the top left here is zeros that are only used to locate the decimal point. So what that means is, like these 2 zeros here, they're right after the decimal point, and they come before any non-zero numbers. So while they are important in the number themselves, um, technically we don't count them as significant. So, we wouldn't want to just take them out, but the way that these rules work is it's essentially just holding a place for these important numbers to come in. And again, I'll make sure while we're doing actual problems to illustrate that. But so zeros that are only used to locate the decimal point, they are non-significant. So go ahead and write non-significant in there. It is important for us to know what's significant and non-significant because we need to be able to tell how many there are when we are determining how many there should be in our answer once we start actually doing the math. So basically, don't start counting significant figures until we get to a non-zero number. All right, now for a little bit trickier one. If you have zeros at the end of a number, so it's after all the non-zeros, and there is a decimal point in the number. So we have a decimal point, and we have zeros at the end here. That makes them significant. If there is a decimal there and there are zeros at the end, those zeros are significant because they're showing us that we actually know what those digits are past the decimal point. If they are there, they're proving to us that we know what is in the thousandth, the 10,000th, the millionth place. If we were to try to go past that, we wouldn't be able to say with for sure accuracy that there's a 0 next. It could be a 1, it could be a 2, but it just didn't round that 0 before it up. So if they are there, that means they are significant and they're important and we want them to be there. So now for the last rule we have for counting significant and non-significant figures is if there are zeros at the end, so we're looking at zeros at the end again, but there is no decimals, this time they are non-significant. So go ahead and write non-significant in there. Now this is what throws everybody off. I always get people who frankly are mad about the fact that if there's a decimal, they're significant. If there's not a decimal, they aren't. The reason this is because when you have a decimal and you show different places in there after the decimal, you're saying that, like I just said, you're saying you know what's in that 1,000th or 10,000th or 100,000th place. When you have zeros at the end here, this easily could have been rounded up. This number could be 45,210, 45,214, but it's been rounded, and so we really don't need those. We know it's in the same spot. We know it's still going to be around 45,200, but taking those zeros away or putting zeros in their place instead of the actual digits makes them not important, which I know probably right now makes no sense, but just trust me and try to get that into your head. If there's a decimal, last zeros count. If there's not a decimal, then they are non-significant, so they're technically not important in the eyes of SigFigs. All right, so let's look at, so now that we kind of know how to count these numbers, we're just gonna just want to recap them real quick. So anytime anything is a non-zero, so a 4, 5, 6, 7, whatever, it is significant. Anytime they are sandwiched, so we have zeros between two non-zeros. So if we have 5, 0, 0, 5, then those zeros in between the 5s are also significant. Trailing zeros if a decimal is present. So those decimal or those zeros that are at the end with a decimal in the number, they are significant. The trailing zeros with no decimal, so the the zeros at the end with no decimal present are non-significant. Remember, these are our weird rules we got to remember. And then, of course, any cosmetic zeros, which are the ones before a decimal place without any numbers, or decimal placing zeros, so the zeros that come right after the decimal before you get to a non-zero number, they're also non-significant. So we've got about 6 different rules here and a lot of bad handwriting, but I know this is quite possibly confusing. That's why we're going to spend so much time on this actually working with it in class and why this video is so long. But it's an important thing to use all year, so we got to get it down as best as we can now. It's something that it takes some time to get used to. So now I want to go ahead and look at the rules when you're actually working with them in math. So we're going to know how to actually count them. You have to know to count them to be able to use the rules that are in math. So back to the point of sig figs is that your answer cannot be more precise than the least precise measurement. If you measure a line and you get it being 3.6 meters, you can't go back to someone and accurately say, oh, this line is definitely 3.6147 meters long if you only measured it to 3.6. That'd be lying. It could be that. It could be one, it could only be one digit off. It could be super close. But when it comes to science, sometimes even down to that 7th decimal place, that can make a really big difference. So we only want to report information to the most accurate that we possibly can without fibbing about what that information is. Even you don't want to round to a farther decimal place than what you actually know is accurate. So that's why we have these rules with this math. So we're going to start with the rules with adding and subtracting, which have to do with significant figures, but it's not as much counting them as it is the numbers past the decimal place. So when you add and you subtract numbers, you're going to use the number of digits after the decimal place and the numbers you are adding or subtracting. So you're always, no matter what math we're doing, you're always going to first look at the numbers that you were starting with. So I have examples that have for adding and subtracting that we're going to work through here, and then we'll have plenty of them to do in class. But you're always going to look at those numbers to start. That's your first step before you determine your answer. So the least precise answer is the most precise that accurate you can be. So in this case, we're counting numbers after the decimal place. So let's look at our addition problem. So we have 4.10 plus 2.2. So before we go and actually solve the problem, again, it's an easy problem, but before we solve it, let's count how many decimal or numbers we have past the decimal place in each number. So in 4.1, 4.10, we have a 1 and we have a 0 after the decimal place. So we have 2, good Lord Almighty, sorry. Pretend that's a 2. Write a 2 above yours so you know what it's actually supposed to say. You have a 2, or you have 2 numbers past the decimal place. In 2.2, we only have 1. So your answer can only have one number past the decimal place because you know what the second decimal place is in 4.10, but you can't accurately say that you know what the 2.2 the next decimal place is. It could be 0, but it could also be 1, 2, 3, or 4 because those numbers would not round up the number 2 ahead of it. So we don't want to assume that it is 0. So when we add them, if you add them together, you get 6.3. And then, so if you include at the end, you have a 6.30, but we only want to include one decimal after. So, because we don't know that second. So this accurately written, not well written, but accurate answer is 6.3. There's only one decimal place here, or at one number after the decimal place here. There's 2 here, but we only want the 1 after that. So this would be how you would do it for adding. It's the same for subtracting. So let's look at subtraction. Hopefully this makes a little sense. Okay, let's look at the next one. We have 10.2, which has one number after the decimal place, and we have 3.2, which also has one number after the decimal place. So in this case, they have the same amount of numbers after the decimal place. So if we go ahead and subtract, 10.2 minus 3.2 gives us 7. But you want one number after the decimal place to show how accurate you know the number is. So in this case, you would write 7.0. That kind of says 7.0. So because you have 1 in each of those, your answer automatically wants to have 1. If that number said 10.200 and it still said 3.2, you still pick the number with the least after the decimal place. So it would still be an answer of 7.0 because you don't know what's after that 2 if it's not given to you. Okay, so hopefully that makes sense. Let's move on to multiplication division so we can get through this video, and I promise I will be there to answer, hopefully not the million questions, but I'm sure there'll be plenty to answer when we get to class when this is due. So Multiplying and dividing, now we are actually counting the significant figures. That's why we went through these rules. And most of our problems that we do are going to involve multiplying and dividing once we get to that math portion in second semester. So you are going to, again, look at the numbers you start with. That's always what you should do. But instead of counting the numbers that go past the decimal place, you're going to count the amount of significant figures in the numbers. And then your answer should have the equivalent to the least amount of significant figures you have with the numbers you start. So let's look at the first example with multiplication. We have 2.5 and we have 2.0. This number has a non-zero here as a 2 and a non-zero as for the 5. So non-zeros we know are significant. So that means this number has a total of 2 significant figures, both non-zero. So hopefully that was easy to count. This one has a 2, so we know that it is significant, but it also has a 0 that is trailing after a decimal place. We know that the zeros after a decimal place that are trailing are significant. So this number also has 2 significant figures, which means that we will want our answer to have 2 significant figures. That's the least amount of figs we have in the numbers we are multiplying. So that's what our answer should have. So if you work it out, 2.5 times 2 comes out to be 5, but we wanted to have 2 significant figures. So we write it as 5.0, because remember, a 0 after a decimal place comes out to be significant. So alright, and let's do one more with this rule on division, and then we'll be home free. So we have 15.0 divided by 3.0. Let's look at 15.0. We've got one significant figure here because it's not a 0, another that's not a 0, so that gives us 2, and then we have a 0 after a decimal, so that means that that is significant. So 15.0 has 3 sig figs inside of it. 3.0, we have a non-zero, so it's automatically significant, and then we know the 0 after the decimal is significant. So this one has 2. So we know, didn't put an equal signs there, sorry. We know that our answer has to have the same amount as whatever the least is that we start with. So our answer, we want it to have 2. So when you divide 15 by 3, you get 5. So again, our answer is 5, but we wanted to have 2 sig figs, so we're going to make it 5.0. So these came out to be the same answer, but we wound up having 2 sig figs to add to each answer, or to be included in the answers. So I know this is not entertaining and not exactly easy to grasp because there's a lot of rules that you have to follow, but this is something that over time, it's something that you're going to grasp, and we're not going to use it a ton first semester, so we will definitely review when we get to second semester. But come to class with questions. Make sure you've written all this down, listen to all this. I'm sorry, this will probably be the longest video we have all year. Apologies for that, but we'll spend time in class and we'll make sure we get this down. So bring your questions, please.